All right, so this is section 7, topic 2 on exponential functions. So today we're going to start talking about a new type of functions. We've talked about quite a few different kinds of functions already, and we're going to review all of those before we add a new one to the mix. So as a reminder, exponential functions, or all functions, can be represented by verbal descriptions, that's words, algebraic equations, numerical tables, or graphs. So first, let's review the two we've been talking about most recently, linear and quadratic functions. So we're going to go through each of these four types for linear and for quadratic. There's not really much to write down in this section. It's really just kind of a recap for you. So first of all, linear functions. You are driving to visit your best friend in Gulfport. Since you have a long drive ahead, you turn on your cruise control. The cruise control keeps your car traveling at a constant rate, that's important, of 60 miles per hour. Because it's a constant rate, we know that that's going to be linear. The situation is represented by the function f of h equals 60h. So your distance, f of h in miles, depends on your time, h in hours. So there's that constant rate, that slope. If we look at it in a table, remember the way we could tell if something was linear in a table was by finding the slope, finding that constant rate of change. It's going up by 60 in 1 hour. And so we do have that constant rate of change of 60 miles per hour. If we check every set of points on this table, we're still going up by 60 miles in 1 hour. Okay. And then on a graph, the way we could tell that it was linear was by looking at slope again, rise over run. And every time it rises 60, it runs 1. So that's how we knew that a graph was linear. Hopefully all of this is sounding pretty familiar to you. So then quadratics, our favorite. So quadratic functions, which we've worked on for a while now, can be represented in all four ways as well. So a verbal description of a quadratic function would be, we used a lot of balls being thrown into the air or an object falling off of a building. So you're observing the height of a ball as it's dropped from a 150-foot tall building. Remember, as gravity, because of the force of gravity, the more time that passes, the faster the ball travels. The ball does not travel at a constant speed like your car on cruise control. So the height of the ball, h, is a function of, or depends on time. The quadratic function can be represented by negative 16t squared plus 150. So there's that squared that makes it a quadratic. If we look at a table, it does not have the same first differences here. We cannot say that this is going down. This is going down by 80 and going up 1, but this is not going down by 80 and going up 1. So it doesn't have that constant rate of change. We'll talk more about what it looks like in a table soon. And then for it to be quadratic. And then a graph is a curve. This is a decreasing quadratic graph, as a reminder, because the ball is dropping from 150 feet. That's my initial height, and it is decreasing over time. Okay, so now let's talk about exponential. So this is new, but we can relate it to things that we already know. So exponential functions, for a verbal description. A verbal description or a word description or a real life scenario where an exponential function would need to be used is that if you were performing an experiment in science class in which you start with 100 bacteria and the amount of bacteria doubles every hour. If something is doubling, tripling, quadrupling, multiplying by 10, multiplying by 500 every time, then that's an exponential function. Just like we talked about yesterday with our geometric sequences, our exponential functions, which are geometric sequences, are multiplied by the same thing every time. So in a table, you would notice that by saying 100 to 200 is times 2 times 2. Here's that doubling that verbal description was talking about. Every time it is doubling or multiplying by 2. And in a graph, an exponential function looks like this. It's a curve, kind of looks like a parabola, but it's growing much more, it's growing at a different pace than a parabola. A parabola, remember, is like 1 squared is 1, 2 squared is 2. This one grows at a much, much, much quicker pace. It looks like it's flatter, but if you notice these numbers, it's getting pretty big pretty quick. So an algebraic, let's talk about what that looks like as an algebraic equation. So use the following steps to write the equation for the exponential function. So guys, I will tell you, when I first started reading these directions, in my mind, there is a much easier way to do this. So I want you to be on the lookout, because know that these notes will come back around to it and they will tell you the way. But the idea is for you to discover the why behind it. So as we're working through this, I want you to be thinking if you could think of an easier way for us to get this equation rather than going through these steps. So pick 2 points. It's helpful to use the y-intercept and the coordinate where x equals 1. Why do you think we might want to use the y-intercept and the coordinate where x equals 1? Tell a neighbor. You're right, they're little numbers, they're small, it's easier, because I said so, because it said so. Yeah, all those things. So first, let's pull the y-intercept. So remember, the y-intercept is where x equals 0. So that would be the point 0, 100. And then let's get the let's get where x equals 1. So that would be the point 1, 200. Remember, through all of this, we're looking for a pattern. So the standard form of a exponential function is y equals ab to the x. Okay, so we're gonna substitute these into this equation to find the values of a and b. First, we're gonna use that y-intercept. So y, 100, equals a times b to the 0. Now I think we're starting to see why we needed to use that 0. Because right now we have 2 variables, but anything to the 0 power is what? Not 0. Anything to the 0 power is 1. So then we just have a times 1, which is really just a. So now we know the value of a. We could take that value of a and put it back in this equation as well. So now we know y equals 100, b to the x. But I want to know b as well. So to get b, I can use my second point and put 200 equals 100 times 1 to the x. Oh, sorry, times b to the first. Well, b to the first is just b. So then I divide by 100. 200 divided by 100 is 2. So I have a value for a. I have a value for b. So I can write my equation. Y equals 100 times 2 to the x. Now, remember, just like we said on geometric sequences yesterday, you cannot change this to y equals 200 to the x. The only way you could change this to 200 to the x is if this was in parentheses, which it is not. The only thing being raised to the x power is 2. 100 is separate from that. So we cannot just put those together, so be careful with that. Let's move on. So let's practice. Let's do one together, and then I'll let you try one on your own. So let's do this one first. The table and graph below represent an exponential function. Write an equation for the exponential function. So just like before, we're going to use that y equals a b to the x, and we're going to pick 2 points. Again, remember, we should pick the point that's the y-intercept and the point that has 1. Now, technically, after we pick that y-intercept, we could pick 2 or 3 because we could square root or cube root, but it's just easier to not have to do that. So I would still recommend picking those 2 points if that's an option for you. So let's start with this one, the 0, 4. So I have the point 0, 4 and the point 1, 12. So for 0, 4, I have 4 equals A times B to the 0. So B to the 0 is what? 1. You're right. So A equals 4. I hope we're starting to see a pattern here. And then we can take that 4 and put it back in. Y equals 4 times B to the X. So then 12 equals 4 times B to the first. We divide by 4. And so B equals 3. So then my equation is Y equals 4 times 3 to the X. So let's check out our next question. Form a hypothesis relating the A term to one of the key features of the graph. So this is my A term. So let's look at that and look back. And then on this one, this was my A term. So I'm going to give you about 30 seconds. I want you to turn and talk to your table about that. What do you think the A term represents? Okay, so the A term does represent the y-intercept. Hopefully we were able to see that. Here the y-intercept was 4. You can see that here, not clearly, but you could definitely see it here, 0, 4. And then on this table, on this one, the A term was 100. So was my y-intercept in the table, or the value where x equals 0. That's what the y-intercept means. So the A term is the y-intercept. And the B term, I'm going to give you about a little less time, about 15 seconds to figure that one out with your group. Do we know where the B term came from? So I'll give you a hint. For the B term, right here, this 3, what happens to get from 4 to 12? Right, you multiply by 3. What happens to get from 12 to 36? Multiply by 3, and 36 to 108. Multiply by 3. So what do we think that 3 represents? We called it something different yesterday. We used an R, and we called it the common ratio. It's what's being multiplied every time. So let's check that last one. For this one, my common ratio should be 2. Let's check over here. I'm multiplying by 2 every time because that bacteria was doubling. So we've now made a conclusion. We don't have to go through these points every time. You can. This is fine. This is a perfectly acceptable method, especially if you have that coordinate with the 0 and the 1. But you could just say that the A is the y-intercept and the B is the common ratio and sub those 2 in. So I want you to try one on your own. I'm going to give you 3 minutes, and I'm going to put a timer up for that, to try this problem on your own, and then we'll talk about it. Okay, I think 3 minutes was a little much on the time. I think we're done. So let's go ahead and look at it. If you need it to pause the video as a class, that's okay. So the table and graph below represent an exponential function. So write an equation to represent that exponential function. So again, we learned some things earlier that we can shortcut with. We can always use the 2 points. So 0, 2, and 1, 1. So you can say 2 equals a times b to the 0. This is equal to 1. So a equals 2, which we could have gotten from the y-intercept. And then for b, we know that y equals 2 times b to the first, then we divide by 2. So this time my b is at 1/2, or my b is 1/2. So my full equation is y equals 2 times, you can put it in parentheses so we know that it goes together, 1/2 to the x. So this is at 2 and it's going up by 1/2. Okay? All right, it's being multiplied by 1/2. So did our earlier hypothesis match? Is this multiplied by 1/2? So 4, it's technically going down, it's technically decreasing. But because from 4 to 2, we're multiplying by 1/2, 2 to 1, multiplying by 1/2, 1 to 1/2, multiplying by 1/2, 1/2 to 1/4, multiplying by 1/2. So every time our common ratio is 1/2. So the answer to that is yes. All right, we're ready for Beat the Test. So let's look at this part. So we're going to match the graphs with the functions here. So remember, we have a shortcut for this. We can identify the y-intercept and the common ratio from these equations. So I know that this one, I know that it has a common ratio of 3, but I'm not sure what that y-intercept is. Any ideas? Yes, so that y-intercept is actually 1 because it's y equals 1 times 3 to the x. Because you can multiply anything times 1 and not change it. So for this one, that y-intercept, that a value is actually 1 and the b value is 3, also known as the r, or the common ratio. So I'm looking for a y-intercept of 1. So let's check these. That's at -2. That's at -1. It's at +2. This is at 1. Let's check to be sure. So from here, that 1 should be multiplied by 3. So at 1, it should be at 3. And then that 3 should be multiplied by 3. So at 2, it should be at 9. This one is correct. So it's f of x equals 3 to the x. Let's go to my second one. So my second one has a y-intercept at 2 and should have a common ratio of 3. So my y-intercept should be at 2. This one's at 2, -2, -1. So this is my only one at 2. It's probably it, but let's verify my common ratio here. My common ratio is 3. So it should be 3 times 2, which is at 6 here. And then 6 times 2, which is at 12, would be at 2. We don't go that high, but it would be up here. So this one is correct. F of x equals 2 times 3 to the x. For this one's a little tricky because it does have this negative out here, okay? If it was f of x equals -3x, then that -3 would just be my common ratio. It would just be my b. But because it's not in parentheses, because it's -3 to the x, this negative is actually a -1. So it's actually written as -1 times 3 to the x. Okay, so one more time, because the negative is not in parentheses, this is not -3 to the x power. It's negative space, okay, 3 to the x power. Negative is separate from the 3 to the x power. Okay, so that's where this comes from. So my y-intercept is actually at -1, so it's either this one or this one. This is at -2, so this one. And then the 3 is my common ratio. So -1 times 3 is -3. -3 times 3 is -9. Okay, be careful. This is not slope. I'm not trying to go over 1 and up 3 and over 1 and up 3. I'm trying to multiply the 3 times my y-coordinate from before. So my y-coordinate was -1, so then I multiply it by 3 and I get -3. My y-coordinate was -3, I multiply it by 3 and I get -9. Okay, so this one is f of x equals -3 to the x. And then last, we have a y-intercept of -2 and a common ratio of 3. So I'm starting at -2. And I should be able to multiply by 3 to get the next coordinate over every time. So I multiply by 3 and I get -6. I multiply by 3 and I would get -18. If you wanted to go backwards, you could to get here. But you would have to divide instead of multiply. So if I was going backwards to -1, I would divide by 3, and that would be at -2/3. So that's why that point is kind of in the middle right there. But you could go forwards or backwards with that. As usual, if you have any questions, please, please, please come see either, let me write this answer, but come see either Miss Rayburn or Miss Golden, and we will be happy to help. Remember, there is no tutoring this week. No tutoring this week. So even though it's Tuesday, we did send out a new tutoring schedule, but there will not be tutoring this week. Okay? Your homework tonight, so here's your reminders. No tutoring this week. Okay? And homework is on, you guessed it, Schoology. So make sure you're doing your homework. We are checking it. We will be putting in those grades. And we will be contacting parents if there is an issue getting homework in. Some of you guys made a New Year's resolution before school got out to get your homework done. So let's stay on top of things. So no tutoring today, and your homework's on Schoology. Let me know if you have any questions. Stop by my room or Miss Rayburn's room. Have a great day.